Good morning. For me, coming to Cargese has many happy memories. I've been coming here probably since the late 90s, but this is a venerable location where the community has been gathering to give talks in physics, probably since the early 1960s, in fact. On one of my visits here, David Pines was here, and he remarked how in the old days they would come here for 6 weeks, and they would hang out at a hotel on the other side of Cargese. That was where it was before they had the center here. I was remembering with Henri Alloul that about 16 years ago, Bob Schrieffer gave a talk in this room. And of course, Bob died just a week and a half ago, on Saturday. And so one can't give a talk on Introduction to Superconductivity without thinking about this incredible pioneer of the microscopics of superconductivity. He was a very great man. He was brilliant. He was on the edge. He was bipolar. And he fought that all his life, but it eventually got the better of him. But he's a great guy, and in a way, I suppose my talks are dedicated to him. Yeah? So, we're going to talk about superconductivity, and this is really the 2nd century of superconductivity. And, of course, it's not a dead field. It's a rapidly developing field. If you listen to the media, we are on the edge of quantum supremacy, whatever that means. Okay? But certainly, the notion of entanglement has entered our field, and there's no more wonderful example of entangled macroscopic behavior in quantum matter than superconductivity. So this is, in some sense, superconductivity in the era of entanglement, hence the title of this series of talks. I'm sorry, what I'm going to do is I'm going to start this talk, and I hope to do this each of my talks, with some PowerPoint, but then I'm going to switch to the blackboard, okay? So don't get too used to the beautiful colors. This is going to be like, well, anyway, we're going to go to black and white very soon, okay? So, here's, unfortunately, I left my little widget at home. This is the outline of what I'm going to talk about. 4 lectures. You could give a 1 semester course on superconductivity. And what I want to do is really to provide a tapas of ideas that will get you thinking about it if you're already experts. But if you're not an expert, we'll give you an introduction, and there will be a way to start reading more about the field. Okay? These talks at this meeting are run on the ICAM style with so-called Frauenfelder rules, which means that you have 90 minutes, but that's not 90 minutes for 90 minutes of intense presentation with no questions. It's actually 1 hour plus half an hour for questions, right? And those questions don't need to be at the very end, although if we want to do it that way, we can. They can occur at any point during the lecture, starting now, okay? Okay, right? So please, and one rapidly learns that often the most innocent question, sometimes even to the expert, the most stupid question, is actually the best question, okay? So please ask questions, okay? So today I'm going to talk about superconductivity at the macro scale, about phase coherence. We're going to learn about the 2 basic length scales in superconductors, that is, the penetration depth and the coherence length, okay? We're going to talk about the macroscopic physics, which is in many ways almost the same for all superconductors. This is the physics described by the Ginzburg-Landau equations. And I'm going to tell you a little bit about the history that led up to that, and then I'm going to talk about the development of the Ginzburg-Landau equations, and hopefully we'll get far enough to talk about not only phase stiffness, the Meissner effect, but also the vortex lattice. Okay, I want to talk about those 3 things. Okay, that's my goal for today. And if we don't get there today, that's great, because that means I don't have to write so many notes, and we'll start tomorrow. Okay, so that's fine. Okay, so Okay, references. Let me just show you some of the references that I've looked at briefly. In fact, this is a great book. Superconductivity, a very short introduction. It's the kind of book, it's just a very thin book, written by Stephen Blundell, who is not only a practicing physicist, he's also a great communicator. And this is full of the history of the field. I don't think there's a single equation in the entire book, but it's absolutely marvelous, and I recommend it to you. I really enjoyed reading it from the beginning to the end, and it was written in 2009, so it takes you up to the iron-based superconductors. Okay? Of course, the classic in understanding practical aspects of superconductors is Michael Tinkham's book, Introduction to Superconductivity. And it's particularly good for the discussion of the macroscopic properties of superconductors. Okay. Next, of course, this is a wonderful book, Theory of Superconductivity. I don't know when Bob Schrieffer first wrote this, but it's based on the lectures he used to give himself about his understanding of superconductivity. It basically revolves around BCS theory. What better person to talk about BCS theory than the man who first wrote down the wave function? Okay, so this is a wonderful book, and it is indeed a classic. But if you want to get more serious, nothing beats AGD. Okay, right? And this book is particularly marvelous in that it uses the diagrammatic method. It starts with Fermi liquid theory. It develops, this was the book that grew out of their own work. The Landau Institute had a principle that you couldn't write papers that developed the technique. That was just forbidden. Who knows why? Okay? The only way you could write a paper that developed the technique was to write a book. And so they wrote a book, and this was the book, okay? And it's particularly a Bible when it comes to looking at the physics of dirty BCS superconductors, and there's a whole section of it at the end discussing that part. And that's the real, I'm not at that level, but that's the real, if you're a true Russian physicist, you know the last part off by heart, okay? And you can do the diagrams, okay? And this is the book which graduate students in the early 60s used to read in the basement at Harvard, because you weren't allowed to use diagrams in Harvard in those days. It was the days of Julian Schwinger, so they'd take this book and they'd read it like a piece of porno down in the basement. Okay, this was the stuff that got them going, right? Okay, all right. So, and then I should be arrested for the next one. This is my book, which is nothing like the same level, but some of the things I'll talk about are in chapter 11, 14, and 15, and you don't need to buy it. As you know, there's a Russian website where you can download all these books illegally, okay? Okay, but I'm not going to tell you about that website, okay? Okay, good. So those are references, and there are also a number of other texts available legally online, which you can read at, which I didn't have time to put down. Okay, we're almost finished with the PowerPoint introduction. So let's talk about superconductivity at the macro scale, okay? And I'll show you a video. It would have been great to show a demonstration here, but getting the liquid nitrogen down here is a bit complicated, so we're not going to do that, but I'll show a video in a minute. But let's talk about the story so far, and it's really been about almost 110 years of superconductivity. This is one of the various pictures you can get online of the evolution of superconductivity over the era. Is this a pointer? Good, okay. Superconductivity first discovered by Heike Kamerlin-Onnes in 2011, okay? And notice the scale here is very compressed up to 1980. So you've got 80 years compressed in the first two squares here, okay? All right. And that's because it's got TC here, and if you didn't do it, it would look like a vertical line. TC has really shot up in the last 50 years or so. So let's go and look at that, the various families. These are the conventional superconductors. The very first superconductor discovered was mercury, and the reason this was discovered first is that, well, they had finally mastered how to cool metals down to very low temperatures. Over the 19th century, people discovered that when you rapidly expand gases, they cool down, and if you keep pumping them round and round, you can cool things down, and gradually they learned how to liquefy oxygen and to solidify carbon dioxide and then nitrogen, and they went down and down and down. But some gases refused to liquefy. Okay, it took a long time before they finally figured out a way, this guy Dewar, to liquefy helium. Okay? And at the lab in Leiden, they were the first lab to really use this for research. And it was Kameninos who first decided he would use his new liquid helium to cool down metals and see what would happen. Okay? And out of that, they discovered superconductivity. And these are the so-called conventional superconductors, marching their way up in TC. Magnesium diboride was technically discovered this century, but you could buy it commercially for years and years and years before that, back into the 80s. But for some reason or other, no one ever cooled it down and tested whether it went superconducting. So it was discovered in the year 2002, long after other key discoveries. Let's look at some other key discoveries. Superfluid helium-4. Well, that's not a superconductor. It's, of course, a superfluid, and was discovered in 1937. Okay? And its discovery profoundly influenced the development of ideas in superconductivity, which is why I put it there. The next one on this little list is there, superfluid helium-3. It looks like it was discovered just after that. From your perspective, it probably was, but actually it was discovered in 1983, and it's unique on this set of diagrams here. It's one of the few that was actually predicted theoretically. Helium-3 was predicted by the theorists to go superfluid in 1960, and they had a theory for it. It would be a BCS, a sort of BCS superconductor, and they made the stupid mistake of estimating TC, which came out to be 100 millikelvin, and the experimentalists tried and tried and tried, and nothing happened, so the theorists were obviously wrong. It's just that they got the exponent wrong by a tiny bit. They also got the pairing symmetry wrong by a tiny bit. Nevertheless, the basic idea was sound, and within 15 years of the original proposal, the experimentalists had got down to 1 millikelvin, and so by 1973, helium-3 was seen to go superfluid at Cornell University. Okay? That's the first superfluid discovered in which in terrestrial matter at least, and I guess excluding nuclei, in which the pairing force is a repulsive interaction, the repulsive interactions between the helium. Okay? In 1979, go superconducting. This is a magnetic material. It's the first of the antiferromagnetic superconductors, and it led to the discovery of a whole family of so-called heavy fermion superconductors, including uranium beryllium-13, uranium platinum-3, and in fact, not long after they were discovered, 1987 came along, and the high-temperature superconductors came, so these were no longer the central focus of fascination. Nevertheless, in fact, in the year 2000, a family of heavy electron systems that are very similar but miniature version of the cuprates were discovered, and you can see TC shot up from, actually, there was one at 0.1 Kelvin, and then 2 Kelvin, and then all the way up to 19 Kelvin, which is this plutonium material. Okay. The cuprates, discovered in 1986, I remember the excitement of the discovery of the cuprates. These are 2D materials, and within the first 3 months of their announcement, TC went from 37 Kelvin to 92 Kelvin. Okay? And at that rate of colossal increase, you thought that by the next year you'd have room temperature superconductivity, but it wasn't to be. You also thought that you might have resolved the question of what makes these things tick 30 years later, 40 years later, but that's not the case either. Because although we know very reliably that these are D-wave superconductors and that their superconductivity is intimately intertwined with antiferromagnetism, we don't really understand the microscopic mechanism of the pairing because we don't really understand the metal from which they're born. It's not a regular Fermi liquid, okay? And so there are a lot of exciting questions still connected with these materials, and in particular, the whole notion of strange metals was discovered because optimally doped YbCO, which is this guy here, 1, 2, 3, yttrium, barium 2, copper 3, oxygen 7, has a linear resistivity. And we'll talk about that towards the end of my lecture series. The challenge of understanding these strange metals, strange metallic behavior is seen here, but also seen here, and also seen here. Okay? So there's some kind of intimate relationship with the superconductivity. Okay? The buckyball superconductors were discovered in the 1990s, and these materials are just buckyballs. And if you dope them with potassium or some other alkali metal, you can drive them superconducting, and the highest TC under pressure is somewhere around 40 Kelvin. They're a very exotic kind of, probably phonon-based superconductor. And then, like another earthquake in 2007, Hosono discovered the iron-based superconductors. He was actually at the time interested in a lot of very weird things. One of his things has been to discover superconducting concrete. I kid you not. That's one of his goals. Okay, if you can make concrete superconducting, you can use it on a large scale. Anyway, he discovered along the way, quite by chance, these iron-based superconductors. These are also layered materials. Some of them are so-called pnictides, containing, for example, arsenic or sulfur. And some of them are chalcogenides, such as the iron selenide family. Some of them have antiferromagnetism, nematicity. Some of them don't have any antiferromagnetism. That's rarer, but still have a very high TC. And I think it's fair to say that unlike the cuprates, where we know the order parameter is d wave, in the case of the iron-based superconductors, there's much more uncertainty. Some people think there are different pairing symmetries for different materials. Okay? And yet, if you go to nearby atoms, to cobalt, to manganese, they don't superconduct at all. So we don't know what's special about these layered systems. Okay? And in my opinion, the current theory is completely wrong, and we'll have to make a new break, and I might allude to that later in my talks, okay? But this is not the end.
It's not exactly covert layers after.
Okay, if you've got someone to keep me honest here. What's? Yeah, probably. Okay, very good. But nothing, they haven't been able to bring it up a lot, right? Okay. And of course, the story's not over with conventional BCS superconductivity. A long time ago, Neil Ashcroft predicted that if you pressurize hydrogen, it'll become metallic and will probably be a room temperature superconductor. In fact, there are two groups now, one in Cambridge, Massachusetts, who did it once, and another group now on the outskirts of Paris that claim they produced metallic hydrogen. No one's tested the Meissner Effect yet, okay? The diamonds tend to break very often. But we believe that once they get it metallic, it probably will be a room temperature superconductor. And in the meantime, hydrogen sulfide, H3S, and lanthanum hydride, which is actually a materials by design material, okay, have both been found to go superconducting at these high temperatures, up to 250 Kelvin, under colossal pressures. Okay. And whilst this is not going to be a basis for modern applications, because we have no idea how you could make a bulk magnet at such high pressures, it is a proof of principle. We no longer think of room temperature superconductivity as an impossible concept. We don't know whether we'll ever achieve it, but we're certainly fascinated to understand what are the boundaries. And whereas back in the 1960s, theorists would confidently predict that you couldn't go above 25 Kelvin. Okay? Now nobody would make such a prediction for ambient pressure superconductors. We just don't know. Okay? But certainly, under ambient conditions, you can get superconductivity well above 100 Kelvin. Okay? And for practical purposes, in fact, above liquid nitrogen temperature is already very, very good. This is, of course, not the end of the story, and we will hear a set of lectures this week by Dmitry Efetov on bilayer and moiré graphene, which is way down here, magic angle graphene. Okay? Magic angle graphene shows the prospects of giving us a new perspective on doped Mott insulators. And in fact, it may well be true that the strange metallic behavior that occurs in these wonderful materials is intimately related to the strange metallic behavior seen in the cuprates and in the doped pnictides. Okay? And so this is a new frontier that's just opening up. Okay? And so, by the way, notice how these discoveries come at random intervals. You never know when the next one's going to come. It's like the next earthquake in San Francisco. We know there will be one. We don't know when it will be. We don't know how big it will be. But superconductivity, like earthquakes, can't be predicted at the moment. But I think it's fair to say that it's unlikely that this is the last family to be discovered. Okay, it would be very weird if we discovered all of them up to 2008 and then there were no more, right? Especially given the vastness of the periodic table. And so I think it's fair to say that this is a very, very active field. It's a field that is influencing technology, both through its influence in superconductivity, but also through MRIs, the new magnetic levitating trains that they're going to build from Kyoto to Tokyo will be high TC superconducting maglev trains. Okay? And so this is a technology that's slowly coming online. This is the second century of superconductivity, and I think it's a very exciting time. But to understand all that, we have to go back to basics, right? I want to learn about high-temperature superconductors. Well, that's like saying, okay, fine, but you've got to go back to basics, learn the roots of your language, go back and learn some Latin. If you want to study European languages, well, we're going to do the same. We're going to look at the Latin of superconductivity, okay, which means that we're going to talk about Ginzburg-Landau theory today, okay, and then we're going to talk about BCS theory tomorrow, okay, and then we're going to come to the modern era after that, okay. Any questions on this?
Not a question, no.
Yeah. A comment. A mark, yes.
I think nowadays we change era in the sense that when you handle material, you have to ask yourself, why isn't it superconducting?
Why isn't it superconducting? That's a good point, yeah. And by the way, mistakes have been made. Uranium beryllium-13 here, labeled as 1983, was actually seen to go superconducting in 1973, but the experimentalists who saw it didn't believe it was intrinsic, so they put it on the shelf. Okay. Right. So let's go back and look a little bit at the early history before I switch to the blackboard. Here is Heike Kamen-Onis, and he did experiments at low temperature. He was one of the first to use liquid helium-3 using the new duos. And in 1911, they saw mercury's resistance go to 0. And this was a momentous occasion. No one really believed it. And to prove it was going on, they actually took a sample of superconducting mercury to England and showed it at the Royal Society, to go superconducting at the Royal Society. I think they kept it cold the whole way. Everyone was pretty impressed because it had been superconducting all the way from Holland over to England. And that's the amazing thing about these things. What do I have to show? Oh, this is repeating, sorry. Okay, good. Sorry, one more time. This is one point I wanted to make, which is that once you can cool down to helium temperatures, you start to discover all sorts of elements of superconducting. And indeed, the Leiden lab went on to discover, I think, certainly tin, lead, and possibly aluminium were superconducting. So this was really a revolution that came from low-temperature physics. And for a very long time, ultra-low temperature physics and superconductivity were the connected area. What do we know about a superconductor based on Kamen-Onis' work? Well, it's just very simple, that once you start a supercurrent, for example, by inserting a flux into this donut-shaped conductor, the supercurrent just stays. It stays and stays and stays. How long does it stay? As long as you keep the magnetic field there that started the current up, the supercurrent continues there indefinitely. And This fascinated the early community, and many great physicists had a go at trying to understand superconductivity between 1911 and 1933. Einstein, Bohr, Landau, who else? Bloch. Before he discovered Bloch's theorem, he had a go at trying to solve superconductivity, and he made some desperate remark about how the one theory you can make about superconductivity is that it will never be solved. The other thing about it is that Einstein put together a beautiful theory. He knew you couldn't think about it as a Drude metal. It was something collective. And he proposed a theory in which you had molecules, strings of molecules forming, and once the current started, the strings of molecules would be moving without resistance, persistently. That was his theory. He thought it was chemical in nature. There were no equations in his paper, which was published in German, but he did believe that a good theory requires a prediction. So he made a prediction, and the prediction was that persistent currents couldn't jump from one superconductor to a different kind of superconductor because the chemistry would be different. And so at Leiden, they set up the experiment, and lo and behold, supercurrents do go from one superconductor to another. So Einstein knew that his theory was wrong, although he hadn't done any calculations. I'm not really sure. He was just an honest man. And he said that, in fact, the life of the theoretical physicist is a difficult one because he or she, didn't say he or she, he said he, but he or she is destined to make many predictions, most of which will be wrong. And that's very important, okay? It's like being an artist. You may not capture the scene all the time. But if you don't make a prediction and you don't make a theory, then you can't test it against experiment and then try again if it's wrong, and it probably will be, okay? And so one of the things we need to go back to in the modern era is to get rid of this fear of failure in the theoretical community. Good theories probably fail, but they might be useful later. Bardeen had 3 theories of superconductivity before BCS theory, okay? All right? And if he just stuck with the first one and insisted, oh, I know it's right, he would have never gotten there, okay? It's very important, this cycle of experiment, theory, prediction. It's not right, okay, it was a good theory, but it didn't work out, okay? That's vital. Okay, so what did they not have right? Well, they were missing experiment. And the experiment was the Meissner Effect. The fact that a superconductor, when you cool it down in a small field, expels that field spontaneously. The field just doesn't live inside it. And Meissner's colleague, Gorta, thought a lot about this. He came to the conclusion, which Meissner didn't entirely agree with, that superconductors cannot have fields inside them. And this became the prevalent idea at the time. In fact, it was true for all of the superconductors they knew at that time. Okay? If you put too much of a field on and you cool it down, it just doesn't go superconducting. End of story. Right? Okay? These are the so-called type 1 superconductors. And so, 1933, this idea was picked up, one more development. In 1937, 2 different groups, one group in Toronto and Piotr Kapitsa in Moscow, were puzzling over something that had been known for a very long time in helium-4. In helium-4, they had measured the specific heat capacity. This is a modern measurement. And they'd seen it has a lambda discontinuity in the specific heat capacity. Great big singularity. At the time, it would have gone up like that, right? But as time has gone on, they've shot helium-4 up into space, and they've looked at it at smaller and smaller intervals, purer and purer samples, and it just keeps diverging, and we understand that. This is not a quantum phenomena. This is classical criticality, okay? Right? Okay. Nevertheless, they didn't know what happened here. They knew there was some kind of hidden order, but they had no idea what it was until someone had the bright idea of trying to measure its viscosity, and they discovered it kept going down, and the more accurate they made the measurement, the better it became, until finally Kapitsa and Allen and Meissner came to the conclusion that actually the viscosity was 0. And they named it a superfluid. And this discovery was strongly intertwined with the discovery of superconductivity, okay? Because they realized that these were 2 things that had persistent currents inside them, okay? Could they be the same phenomena? And so the breakthrough that was made in 1937 was by Fritz London. He'd been working a bit with his brother, Heinz London. They were émigrés from Germany. First, they were working on this idea in the as to Henri Poincaré, but then the money ran out and they moved to England. I guess other things were also starting to happen. And in Oxford, they worked on the idea some more. And Fritz then eventually wrote it up and sent it off as a letter to nature in 1937. And in those days, they were still calling them superconductors, okay, which was a direct translation of the Dutch, which did not mean superconductor. It was something that was above conductors. But of course, this was the age of Superman, and so it wasn't long before supraconductor became superconductor, okay? And in fact, Blundell in his book talks about this. He says that, you know, of course, a man who wears his underpants over his blue trousers is pretty weird, okay? But superconductors were just as weird to physicists as Superman was to the regular public, okay? So this is the equation that he wrote down. We're going to come back to that and how he derived this equation, okay? But before I move away from my PowerPoint, so the point is, this was derived on the basis of one-particle quantum mechanics, and we'll come back to that. You may know that in one-particle quantum mechanics, the kinetic term, which is momentum squared, becomes gauged and becomes P minus EA squared. So in the Hamiltonian, there's a term which goes like A squared, and if you differentiate the Hamiltonian, you get the current. It's then linear in A, and if the rest of the stuff is irrelevant, if somehow the wave function is rigid, so that it stays the same when you turn on a field, London reasoned, you'd get this equation. And this London equation, which is not gauge invariant, needs to be in a fixed gauge, then predicts the Meissner effect. We'll come back to that in a moment, okay? But before we do that, let's look at the Meissner effect in action. And of course, I can't demonstrate it here, but London never really saw the Meissner effect before his very eyes. He'd have had to cool things in helium. The doers were not transparent. He just knew it was an experiment. For him, it was almost theoretical, but we can watch it, okay? And if we had the equipment set up here, in fact, since this stuff is ceramic, I've done this myself, you can make very thin films of ceramic high-TC superconductor on top of silica. They're about a micron thick, these films, okay? And they superconduct perfectly. You can wrap them up and put a little bit of sponge inside there, which absorbs the liquid nitrogen. You dunk them in the liquid nitrogen. They stay cold for 5 minutes, okay? And you can grab them with your hand and mess with them, okay? And it's absolutely amazing because you see superconductivity before your very eyes and you feel the force of superconductivity. This is an outreach guy from Israel. They do this really well at the Hebrew University, and this is a TED talk he gave, and I just screen captured it. You're not supposed to do that, but I did it. And here he is. Look, there it is. Look at that wonderful phenomenon. It's utterly amazing. Okay, that's a big air gap there. Okay, of course it has all this smoke behind it, which makes it look really amazing. Okay, and he talks about how this is quantum mechanics before your very eyes. Of course, everything is quantum mechanics before your very eyes. Okay, and so this is what everyone expected you could do. This is the effect of the Meissner effect. But I think before high TC was discovered, no one expected the next experiment to work. And I don't have a very good clip of this, but let me just show you the next experiment. It's upside down. Okay, how is that possible? Let's look at the demo of that working. So he's got it on there. He's cooled it down. He picks it up. Doesn't slide off, and he inverts it. It still stays there, and then, as all good, there it is. It's a TED talk. So it went past very quickly, but it can go upside down. This is a commercial thing. You can buy one of these for a couple of £1,000, and it's amazing. How does it grip that piece of superconductor? And you can do this with a magnet. You can levitate it like this, and you can hold it sideways. You can shake it, and it doesn't come off, and you can pull it, and you can feel the resistance. It's gripped by the superconductivity, okay? This is much more than just levitation. It's gripping it there, okay? How is that possible? Well, let's make a little diversion on that before we go to the blackboard. Of course, the Meissner effect is a property of all superconductors. They expel a magnetic field, and if you put them on a surface, A magnet will levitate, or you can do it the other way around. You can put a magnet down below, and you can put a superconductor above it, a piece of metal, and when it goes superconducting, it would levitate like that. And in fact, niobium or mercury, you could, in principle, do this experiment, but you'd have to keep it really cold. But if you tipped it over, it would fall off, okay? The suspension stuff is a property of type 2 superconductors. And type 1 superconductors, as we'll discuss, have a very simple phase diagram. This is temperature, this is magnetic field, and there's this region where they form a Meissner phase. No magnetic field penetrates them, okay? But most of the modern superconductors are very different to this. They are type 2 superconductors, and they have the property that their coherence length, if you like, the size of their Cooper pairs, is much, much smaller. And when it becomes smaller than the penetration depth, something amazing happens. In fact, they can absorb magnetic fields, but only in the form of flux quanta. And these flux quanta have at their core, like a great big hurricane vortex, a normal state where there's no superconductivity. And this normal component loves to pin if you've got disordered systems. It just sticks there, okay? And so the picture that you then should have in your mind of what's going on is this picture here, that when you have this levitating superconductor, it lets some of the magnetic fields penetrate in the form of these vortices, these quantized vortices, and they're pinned there. And so in terms of macroscopic physics, this is a hybrid system. It contains both a diamagnetic component, perfectly diamagnetic, but these little guys here are like little magnets, little bar magnets sitting in it, pinned inside, very, very strong. And these are the guys that give you the attraction between a south and a north pole, and the diamagnetism provides the stability. If you do that with a regular magnet, it'll either fall below or it'll just clamp up, right? But because there's a diamagnetism there, that provides the feedback. It doesn't let it come too close or go too far apart, makes the well stable. And as a result, you can just grip this thing. So it's a combination of old-fashioned magnetism plus superconducting diamagnetism that makes this possible. And it means that if you tip one of these guys, it doesn't fall off, and you can turn it upside down, which, of course, I didn't have a good demonstration of that. Okay? So maybe we'll come back a little bit later to my view graphs. I've got one worked example to show you a little bit later. Oh, we've got one more thing. Haha. I forgot this. Okay. Before we start, I don't know how it is for you, but at my school, we're supposed to interact with the class, and the one way you do that is you have clickers, okay? And you put up a question, and they have to answer it. They click it, and we measure who answered what question, and it gives you some idea about your audience. So I thought I'd expose you guys to the same thing. We don't have any clickers here. You can just put your hands up, okay? And it's quiz time. Quiz time. So here's the little question, which actually motivates what we're going to do next. This is your little exercise. We get a metal, like copper, an insulator, like glass, any insulator you like, and a superconductor. And we expose each of them to an instantaneous electric field pulse, a delta function, okay? E of t equals big E times delta t. So it clicks on, and it's gone, okay? Right? And so the question is, what current evolves afterwards in the material, after that delta function pulse, after that little impulse that you apply to it? What do you think it is, okay? And of course, in our minds, we have these pictures of two different pictures of metals and insulators. A metal has electrons bouncing around, they're free. They're moving at an immense speed, but like a swarm of bees, they remain stationary, kind of bouncing off trees and all sorts of stuff, very angry, but they stay there. And when you apply an electric field in this direction, this starts to drift along, right? And you get a V drift. And the other picture that we're used to is that in an insulator, we have a background of positive ions, and bound to each of these are localized electrons. These are pictures of insulators and metals, and the question you can ask is, okay, well, what happens if I just kick them with an electric field? E of t is just a pulse. In other words, the electric field looks like this. Here's t equals 0, and the electric field is a great big, sharp pulse, an impulse. What do you think happens afterwards? And here are your 3 options. We're going to take a vote on it. Okay? Those are your 3 options. They are all slightly different. Okay? This is like a multiple choice question. Okay? Which do you think is the right one? Okay? Study them carefully. Had enough time to study? Okay? Okay, are you ready to vote? Okay, this is our vote now. Who votes for A? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They're all going up. 13, 14, 15. Anyone hasn't voted? 16, 17? Come on, you've got to get, it's your last chance to vote. 18? More? 19? Okay, good. Are we done with A? Good. Okay, who votes for B? You're not allowed to vote twice. Put your hand down, okay? All right, 1, 2, 3, 4, 5, 6, 7 maybe? 7, 8? Okay, what, 20? 9? 9? We're not getting close to number. I got yours, 9. Okay, sorry, you didn't win. Okay, last one. C. Who votes for C? Okay, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have a tie. Okay? Could be that A and C are both wrong, and B is the right answer, of course, which proves you should never do things by referendum, as if we didn't know. Okay? As if we didn't know. Okay? Fortunately, we do physics, not politics, and the right answer is C. Okay? Right? The right answer is C. And let's go through it. Okay? The point is that in a superconductor and a metal and an insulator, you give it that short, sharp pulse, bing, and during the time the pulse is on, the electrons are accelerating. They don't know they're in an insulator, or they're in a metal, or they're in a superconductor. They start to move. Okay? And at the end of that pulse, they've got momentum, equals force times time, right? Okay, therefore they got velocity, therefore they got current, therefore they're moving, okay? And they're all moving with exactly the same amount of momentum. They all have exactly the same mass, exactly the same charge. So therefore they all have exactly the same current here. Okay? And that's called the F-sum rule in condensed matter physics, because that delta function tells you that the sum over all frequencies of response equals the plasma frequency squared. That's called the F-sum rule, right? It's only what happens next that decides whether you have a superconductor, a metal, or an insulator, okay? So the current decays in all of them. In an insulator, the time scale for it, okay, for a metal, the time scale for it to decay is the transport time, okay? It's the VFT equals the mean free path. It's the mean free path divided by the velocity, okay? In the superconductor, the normal electrons also decay, but the left over behind part, the superconducting electrons, the condensate, doesn't decay at all. It just maintains its velocity. Whereas in an insulator, what do you think determines the time scale of decay? Anyone know? What do you think? Who voted for C? Yes?
Maybe similar in the dielectric.
Well, I suppose that's sort of true. I would say it's the inverse of the gap size. That's an energy scale, so h bar over the gap is a time scale, okay? Interestingly enough, both a superconductor and an insulator have a gap, okay? And so there probably is a rapid response in a superconductor too, but what's left behind is the response at zero frequency. So we're going to talk about this. This is really the basis. This is London's picture of the superconductor. In order to understand a superconductor, we need to go beyond these simple pictures here. Okay? and look at the quantum mechanics of current before we go on to greater details, okay? That will lead us to the Ginzburg-Landau theory and the macroscopic understanding of these remarkable beasts, okay? So before I take away my view graphs, any questions? Yes? Yes? Yes. So, no, they're not always pinned. And the cleaner you make them, the less well they're pinned, okay? But if you don't pin them, if they're not pinned, you don't get a superconductor in a vortex lattice. So the pinning is very, very important. Because if they move, there's dissipation. The cores dissipate, you have a residual resistivity. And so, for example, in the cuprates, when you raise the magnetic field above the upper critical field, which is kind of badly defined, you get a vortex liquid. And these things move around, and although there is some local superconductivity, they're not macroscopic superconductors anymore. So that's a really good question. Any other question? Yes? They would have a resistance. The current would actually just decay. You wouldn't see that they were even diamagnetic, except that, a metal is diamagnetic. If you put an AC field on a metal, it levitates beautifully. And if you go to Shanghai, that's how that levitating train works. It uses AC current. It doesn't use DC current. Okay. Actually, I guess let's forget that. That's not true. It has a DC magnet, but it's a conventional magnet. Yes. Question.
You still have some time before, it can still move around until it heats up to DC, right? That's the heat dissipation, right? You generate heat until you push it above DC. That's what it's superconductor.
In a superconductor, you don't generate heat.
No. When the vortex is going.
You're probably no, because I think the moment the moment the fluxes move, you don't get a conventional diamagnetic response. So I think there'd be no time, no macroscopic time anyway. They're just they're metals.
Because I thought the motion, causes dissipation, generates heat, but I thought that the heat.
No. It's not the heat. They are in the ambient state at that temperature, not superconductors. If you've not got pinned vortices, you require pinned vortices to have superconductivity in a vortex lattice. Okay, good. Let's go on. All right. So now I need to turn this off, or at least blank it out. How do I do that? Good question. Apple 1. Display connected, mirror displays. I just do it so we can turn it back on later. That's it.
But it's fast.
Okay, all right, very good. All right, so we're going to talk about London's picture of London. Do I need to not go beyond that line? Is that why that's there? Oh, I'm gonna.
Wait, so then how do you explain the melting vortex lattice?
I'm not going to try and explain them right now. That is the sort of question that takes me out of my comfort zone at the moment. Okay, all right. So I'm happy to address that afterwards, but right now I would completely screw it up in detail. All right. Okay. So these are our two archetypal pictures. The metal has of course, obeys Ohm's law, and we normally write that J equals sigma E for an isotropic metal or an insulator. Okay, and in our simple Drude picture of conductivity, the swarm here has a characteristic mean free path, which is the Fermi velocity times the scattering time. Okay, and in the Drude picture, sigma equals n e squared tau transport over m. Okay, let's draw that little picture we had before of the donut. Here is our donut of stuff. Okay, and let's imagine that we put a solenoid to the middle and we turn on a magnetic flux. That's B dot ds running across this area here. Okay? Then, of course, we know from Michael Faraday's law that the induced EMF around here, running round here, is equal to minus d phi by dt. So if I suddenly turn that on, I, of course, create an electric potential, electric field running around here. If I put that up, the electric field points in this direction. Okay? And we can also write that. Remember that let me remind you a little bit in magnetism that B is the curl of A. That's a very important relationship for us. Okay? And the integral of B dot ds across this area here, this is ds pointing up like that, and B is running through also, that this is also equal to the integral of A dot dr round, this is across, around this loop here, running that way round. Okay? Okay? And so if the vector potential is uniform, then this is the flux, and this is A times 2 pi r. Okay? And so E equals d phi by dt is equal to minus A times 2 pi r. Okay? And the electric field, if I now suddenly turn on in this thought experiment an electric field, I'm going to write it as minus A delta of t. Okay? That's the, then of course, this is exactly for the period in which I've got the, when I turn on the flux, so if the flux is equal to, the flux as a function of time is just phi times a theta function of time. We just switch it on like that. Then, of course, what that means is that we create a delta function electric field. Okay? And perhaps this isn't too surprising, because you may also remember that E can be written as, that from Maxwell's equations, that the curl of E is equal to, help me out here, the curl of E is equal to minus dB by dt, that when we write that B is equal to the curl of A, we're able to deduce that E equals minus dA by dt. Okay, there's also a term like that. So that if I suddenly turn on a vector potential, then I get a delta function in E, and it looks like that. So A here is the vector potential I suddenly turn on, right? Okay, and so dV by dt, of course, is equal to E times E over m, the force divided by the mass. Okay, and therefore the velocity afterwards is equal to minus EA over m theta of t. Okay, it just jumps up, and therefore the current density, which is NeV, is minus NE squared over m times A, and we can make it a vector equation. This gives me the perfect diamagnetism of an electron fluid. If I give it a pulse of electric field, if I suddenly turn on the vector potential, okay, I get a diamagnetic current. If you prefer to write this E0, then you could have put E0 here, but I wrote it like this to connect up with London's equation. It was London who first realized you could think of the current in this way, okay? And so with this picture, and my blackboard style needs to improve a little bit here, so let me just erase a few things here just so I've got things. So it's this little discussion that gives us the current versus time here, and tells us that we start out at minus n e squared a over m. Everything starts out here, okay? But of course, in a metal, another way to write this is to write this as n e squared over m, 1 over tau transport. And that's useful because you can bring in frequency, and you can write the frequency-dependent conductivity in this little form here. And the nice thing about that is that the real part of the conductivity is then a Lorentzian, and of course the current in a metal, J equals J naught e to the minus t over tau transport. And so it decays like this. This is the characteristic transport scattering time determined by the scattering off disorder and whatever, right? In a insulator, it comes down really rapidly. And in a superconductor, to a first approximation, it doesn't do nothing, okay? So it's this simple picture that we need to understand, okay? And the thought experiment, which is a very useful one that we'll come back to, is a thought experiment of turning on a flux. You turn on a flux, you create a vector potential that rotates this way. A equals phi over 2 pi r, points that way, okay, times theta of t. That vector potential switches on and stays for all time. And in a superconductor, weirdly, so long as that vector potential is there, the supercurrent remains, okay? If you now switch this off, then the vector potential will go back to 0, and the current will go back to 0. But so long as it's on, it maintains its behavior. This configuration is a very useful one, okay? What we'll discover is that the persistent current is in some sense related to a twist of the wave function coming from the vector potential, okay? But this is the picture I'd like you to save in your mind. And now let's look at London's argument that was based on this setup. And we can even look at London's improved argument. But here's the argument he presented in 1937, okay? He said, well, look, just imagine I'm dealing with a quantum electron, one electron for the sake of argument, okay? We know that when an electron moves, it moves according to Schrödinger's equation. And Schrödinger's equation has, we interpret psi squared as the probability of finding an electron at a given point, okay? The total integral of the probability is constant, and therefore the probability obeys our continuity equation, and we know that d rho by dt is equal to minus the divergence of the probability current, okay? And you can work it out. That probability current is nothing more than psi star over m, and then you have this minus I, and for technical reasons, we'll do a backwards-forwards gradient, minus EA psi, okay, of x. This is the vector potential of x, and backwards-forwards here means gradient forwards minus gradient backwards divided by 2. This is what we learned from one-particle quantum mechanics. And this was the point that London made. He said, well, of course, the current, the electrical current, is E times J probability. Okay? Right. It means it avoids me, it means, okay, you're forcing me, it means psi minus I h bar grad, sorry, it means I have to write it in minus I psi star grad psi over 2 plus I h grad psi star psi over 2, okay, minus EA, okay, so the current is then E over M times this, okay? Good question. You can get away without the symmetrized thing, but it gives neater equations if you do it that way. Okay, good. And so this is very interesting because in both classical and quantum mechanics, when you want to introduce the vector potential, you have to, electromagnetic field, you have to introduce it via the vector potential. Quantum mechanics and classical mechanics depends on the vector potential. And of course, the vector potential is not a directly observable quantity. It's only its curl, it's only its time derivatives that determine physical quantities. And of course, this current, although it's physical, has a gauge invariance to it. It has the remarkable property that if I take psi to e to the I alpha times psi, and I take a to a, and I'm going to get this wrong, minus e over h bar grad alpha, that this is unchanged, right? Okay. So if you look at this, it's rather interesting. There's a term here. Let's write this out. We can divide the current in this system into two parts. A part which depends on the gradients of the wave function, minus I h bar e over m, psi star grad psi minus grad psi star psi. And there's another term, minus e squared over m, psi squared times a. Okay? And so we now call these terms, we call this the diamagnetic part of the current. And we call this the paramagnetic part of the current. And in a given gauge, we can divide it up in this particular way, right? So when you switch on a vector potential, immediately after you've switched it on, the current, the wave function hasn't changed, hasn't had time to change, and you get this diamagnetic part. So that's this bit here, the same for all fluids of the same particle density, right? But what happens next is that the paramagnetic part, which points in the opposite direction, starts to switch on. And so you can regard all of these systems at the superconductor is the one where the paramagnetic part does not switch on. It just stays zero for whatever reason. Okay? And so London didn't know why it stayed zero, but he said, look, experimentally, it does stay zero, and so the wave function has a kind of rigidity, okay, such that the paramagnetic part, if I turn on the vector potential, the change in the wave function up to order A is zero. There might be terms of order A squared, but there are no terms of order A, he argued. If there are no terms of order A, then to order A, this is the current. And so he said, well, let's write J equals minus E squared over M NSA, where NS is the density of electrons. Now, of course, there's a sleight of hand going on here because at the beginning, I sneakily told you, let's just imagine one particle. Then I just said, okay, well, let's take this equation and imagine it holds for all the particles for whatever reason. Just scale it up and replace psi squared by not the probability, but the number of particles times the probability density equals the density of superconducting electrons. This was the equation that London wrote down in 1937. And the cognoscenti in his audience, who would have known that it's not gauge invariant, would have told him, but that's not, but Professor London, that's not a gauge invariant. And he would have said, okay, well, that's true. We have to choose a gauge and set the gauge. So let's choose del dot A equals 0, okay? And so in physics, we call that the London gauge, okay, right? Okay, and we often use it. It means that there are no transverse components, no longitudinal components to the vector potential. It's only transverse. If you Fourier transverse pose it, del here becomes Q. So Q dot A is 0. That means it's a transverse field. It's perpendicular to its momentum. So going a little bit further, of course, what this then means is that if the paramagnetic part of the current remains zero due to the rigidity of the wave function, then we can just look at the consequences of this, okay? And of course, the consequences of this are that if we now use Maxwell's equations that tell us that the curl of B equals mu naught J, and we plug in this little equation here, this is then minus mu naught E squared NS over M times A. If we now take the curl of this equation, the curl of B, which makes you dizzy until you remember that this is equal to the gradient of the divergence of B minus grad squared of B, and then you remember that there are no monopoles, so this term is zero. So if I take the curl of this expression here, I then get minus equals minus grad squared B equals minus E squared mu naught NS over M times curl of A is B. And so putting all of that together, we have that grad squared of B is 1 over some length scale, as it must be by dimensional analysis, times B, where this length scale, lambda, is the London penetration depth. 1 over lambda squared is E squared mu naught NS over M, okay? Or if you want to write that out in the form I can never remember it, lambda L is the square root of M over E squared NS mu naught. This is called the London penetration depth. If my watch is right, we have 10 minutes left, but we started 10 minutes late. So we actually have 20 minutes late. 20 minutes more, right? Okay? Or you just cut me off and we have half an hour of coffee. You have to decide, okay? All right, so we've got as far as the penetration depth here. And yes?
Can you switch the lights with the back side of the board? Is that easier to see?
Is it impossible?
Yeah, it's impossible.
Okay, sorry.
We put this vertical.
Okay, so I'm sorry about that. So the point is that when you turn on this magnetic field here, it generates a current. That current, however, lies within a distance lambda inside of the surface of this superconductor. If I had a color, which I'm not going to use it, but the point is if I take a cross-section of this superconductor, of this donut here, here's the cross-section, then within this length scale here, 1 over lambda L, okay, the field decays, and outside the field is finite, but inside the field is zero, okay? So a magnetic field only penetrates a distance lambda L into the superconductor, okay? If you solve this in one dimension, you just get B equals B naught e to the plus or minus x over lambda L, okay? Which means that it's decaying over length scale lambda L, okay? Okay, so fantastic, but what is psi here? We assumed it was just a single particle, and we also assumed it was one, whereas we know we have 10 to the 23 particles in a mole. So what went wrong here? And London was very confused by this. He knew about helium-4, and he'd already proposed that helium-4 was a Bose-Einstein condensate. But he knew that electrons obeyed Fermi statistics, and as a result couldn't condense. And so he didn't know what to do, but he said, look, imagine that the rigidity is the most important part. And he had an upgraded version of this derivation, which is the same derivation, but with psi replaced by x1 through xn, where n is 10 to the 23, okay? And you can basically decorate this equation with sums over particles, okay? It doesn't give you a great deal more insight, but you can then say, well, let's suppose that the paramagnetic part doesn't develop when I turn on the vector potential. And then I get this bit too. It didn't solve the problem, but it was a start. And this kind of reasoning was tremendously influential in the development of superconductivity. And we haven't really gone a long way beyond this equation here. Okay? What we'll do is that actually we will take the same equation, but now we will put in the gradient of the phase in here and decorate this with an h bar over E. That's the right equation for now gauge invariant version, where this is the phase of the superconducting condensate. Okay? It still doesn't tell you what is psi. Okay? But it turns out you can do an awful lot without actually knowing what is psi. Okay? And the Russian school in the late 1940s and 1950s did exactly that. They became so attached to the resulting theory, they began to think of it as microscopic. And we'll talk about that, okay? Right. Okay, so that was London's argument. And let's now talk a bit more about length scales and superconductor types, because we need to talk about this. So I'm going to draw a great big arrow across the top of the board. And we're going to talk about length scales. So obviously a material depends on what length scale you probe it at. We live in the world where we can see things down to a micron size. Of course, with STMs and X-rays, we can see down to the atomic and subatomic level. But our macroscopic world ends at the scale of order of micron. If you go to a machine shop, the best you can machine is about a micron if you're really, really good, okay? And so let's talk about length scales here. This means length scales from 0. I'm thinking about the physics or the correlation functions as a function of separation, okay? And the important thing about a superconductor is it has, first of all, it has a penetration depth, which I'm going to draw here, okay? And it also has a characteristic size for the physics, the microscopic physics, which is the coherence length, which I'm going to draw here for the moment. Okay? And the point is that this is a type 1. Okay, the point is that on length scales longer than lambda L, there's no field. B is equal to 0. Okay. There's also another relevant scale, which is the coherence length. And in BCS superconductors, this is the size of a pair. Okay? It's basically VF divided by the gap of the superconductor. But if you didn't know that that was the mechanism, it could be something else. For example, it could be a charged bosonic condensate. Okay? In fact, a charged bosonic condensate lives in the world we are living in. They're right inside you. Where are they? Where are the charged bosonic condensates inside your body? In fact, everywhere. In the nucleus, because the nucleus has strong pairing between nucleons. And this is the origin of the even-odd asymmetry in binding energies. It's the reason why 238 is stable, and it takes a 1 million volt neutron to split it apart. And it's the reason why 235 is unstable. And I shouldn't be saying that. Anyway, so so this is the characteristic coherence length, okay? And inside this length scale here is the internal machinery of pairing. Okay? And in fact, the picture I've drawn here is for a type 1 superconductor. Okay? A type 1 superconductor has the property that, as I mentioned earlier, that if I draw temperature versus field, that the phase diagram just looks like this. Okay, here you have the Meissner superconductivity, and the field is expelled. Okay, and up here we have regular superconductivity. We have a normal state, normal metal. There is another type of superconductor, and this we'll see that this works. There's an important, so there are two length scales in a superconductor. One is the penetration depth, lambda, and one is the coherence length, psi. And we often characterize these things by a thing called kappa, which is the penetration depth over the coherence length. Okay? So for this superconductor, kappa is less than 1. Okay? And in fact, it turns out that provided kappa is less than 1 over the square root of 2, where does that come from? We get type 1 superconductivity. Okay? But if kappa becomes larger than 1 over the square root of root 2, we get a different situation, which I can just draw it like the same thing round, where psi is now smaller, is down here, and the penetration depth is bigger. Okay? This is a type 2 superconductor. Okay? And in this situation, the phase diagram looks completely different. You have this situation where you have the Meissner here, and you have a vortex lattice here. This is HC2, and this is HC1. And this is TC, this is TC. Okay? So if you want to draw a picture of this system, then in here, what happens is that if I have a superconductor like this, the field is still partially expelled, but some of the vortex lines compress into these vortices that come through. And we'll see that these vortices are quantized. Okay? And moreover, they form a vortex lattice. It's kind of a triangular lattice that looks like this, going through the sample. Each one of these guys has a flux equal to h over the charge of the pair, which we're going to write as E star, but which we secretly know is 2e from microscopic pairing. Okay? And so what happens is that an amount of flux concentrates down, and the core of these vortices is, anyway, it's something like that. We'll come back to that in a minute. Okay? And so this occurs when kappa over L over kappa is greater than 1 over the square root of 2. Okay. Let's make a little table of some well-known superconductors, what their kappa is, and then we're going to turn, and I'm going to just end today by introducing the Ginzburg-Landau Lagrangian or free energy, and that will start next time. So the point is that the pairs of this size, here we will have little pairs, but below some length scale of order psi, you can think of the electrons as being paired up, if it were a BCS superconductor. Okay? And most BCS superconductors, psi is much bigger than lambda L, and this is the reason why BCS themselves never thought of this as a kind of Bose-Einstein condensation, because the bosons were massively overlapping. Millions of bosons overlapping one another. You couldn't think of them as tight little bound states. However, high-temperature superconductors, you can have much smaller coherence lengths, and you can almost think of them as a kind of Bose-Einstein condensate. Indeed, you can actually see indications that the pairs are present above TC in those systems. Okay, so let's make a little table. Well, let's look at lead, some type 2, type 1, some elemental superconductors. Lead and aluminium, type psi in nanometers, lambda L in nanometers, and TC. Those are the only type 1s I'm going to talk about. Aluminum has a coherence length of 1600 nanometers, and a lambda L of 16. I got them the wrong way around, sorry. It's got to be much... Wrong way around, sorry. You can see I did these quickly. Xi is large, 1600, and lambda L is small, 16. And this guy is 83, this is 37. These have TCs of 1.2 and 7.19 Kelvin. Okay, niobium is an elemental type 2 superconductor, and it has a coherence length of 38 nanometers and a penetration depth of 39 nanometers. I don't know whether those are exact numbers, and it goes superconducting at 9.26 Kelvin. Okay, and I've got a whole bunch of interesting compounds now, which we can talk about. For example, YbCO, ytterbium, barium 2, copper 3, O7 plus minus X. Okay, this is a type 2. Its penetration depth depends on directions. It's somewhere around 80 to 100 nanometers. Okay, but its coherence length is about 1.4 nanometers. Okay, just a few unit cells. Okay, and of course here its TC is 92 Kelvin. Here's a few more for you. Barium, cobalt, iron, arsenic, 2, 122, 122, 1 minus X, cobalt X. This has its claimed 2.8 and 200 nanometers. And last but not least, cerium, cobalt, indium 5, which is a miniature high TC superconductor. This has 4.7. This has 280. And these here are 25.3 and 2.3. And I wanted to put magic angle graphene on here, and I couldn't find the numbers. Dimitri may know them, but I don't know what the numbers are. We know what TC is. Do you know what Xi and lambda L is for those cases? 50 nanometers for Xi. 10 to 15. Which, of course, is smaller than the unit cell size. Okay, so it's about the same. Okay. And what is lambda? Do you know?
I don't think anybody knows.
You did. I will tell you how you can get it from your data. Okay, good. So we're basically I think I've got 5 more minutes to go. I'm going to wrap up. It's a natural point for me.
It's good that you wrap up now because we also need to make a short announcement.
Good. All right. I want to point out that although I'm wrapping up now, I'm owed 5 minutes. Okay? Because we started 10 minutes late. Okay, so next time we'll talk about Ginzburg-Landau theory in detail, okay? And we'll use that as a segue to talk about BCS theory. But if you have any questions, you can catch me afterwards. You can also talk to me in the afternoons. I'll be around, and otherwise we'll meet again tomorrow at 9 o'clock. Okay, cheers.